as David mentioned, I'm from Phase Change Energy Solutions Australia. We're kind of a subsidiary of the US company Phase Change Energy Solutions, and we represent them here in Australia to get this really interesting product into the country and to get people to really understand how you can much better design a building. Obviously, we know that we've got an energy problem. We keep burning up our resources, and it costs a lot of money, and we don't want to keep doing it. So some clever scientists, probably about 30 years ago that I've heard about, were using phase change materials to try and stabilise temperatures. A phase change material is simply a material which takes advantage of a fundamental principle, and that is that it melts. If you take a block of ice and you put it inside a glass of Coke, what happens to the Coke? It gets cold. But what happens to the ice? It doesn't get hot, does it? Okay, that's the fundamental principle that we use in phase change material. The ice doesn't get hot, it just transitions, and it's the transition that all of the energy is used. So what phase change materials are is materials that absorb and release heat at predetermined temperature ranges. If we take ice and we put it in our home, and we take it out of the fridge and we put it in the room, it does keep us cool in summer, but it's too cold and it melts quickly. And it's no good to us in winter. If we melted something that was very hot, say steel, at 1,000 degrees, then it would actually also phase change from a solid into a liquid and absorb a huge amount of heat while it turns from a solid to a liquid. That's another phase change. Who can think of another phase change that happens almost every day in our work environment? Anybody? Air conditioning. The liquid that goes through the coils in the air conditioner evaporates into a gas, which is a phase change. And then we take it outside and we squash it back into a liquid again and release the heat outside. Okay, it's a phase change. If you take a pot of water and you boil it on the stove, it hits 100 degrees, it doesn't get hotter, does it? So it's absorbing heat without getting hot. It's another phase change from a liquid to a gas. So phase change is not a new idea. The new idea is that it can be put into a package that you can put into your building and it stays stable for a very long time. That's the challenge that's been out there for a very long time, is to actually make phase change material into a building material. So the engineers in the US thought, how will we do this? They looked at using salts, because if you put salt in water, it changes its freeze point. They looked at using animal fat, but they thought that would be socially unacceptable. If you look at the fish and chip shop and you go there, you see the solid mass on top of the fryer, and they heat it up and it melts. Okay, it's phase changing. You take soap and you heat it up, it'll melt in your hands. It's phase changing. You take chocolate and you put it in your mouth. What happens? Yeah, it melts. It's phase changing. Okay, so lots of things phase change. So they looked at salts and they looked at petroleum products such as paraffin wax. You take a candle and you heat it up. What happens? It melts into a liquid. It's another phase change. Some manufacturers in Germany, such as BASF, I think, and DuPont, developed phase change plasterboard. So they took plasterboard and they impregnated it with small balls of paraffin wax, candle wax, and they would put these plasterboard sheets on the wall and have an incredible building performance improvement. The dilemma with it is that if you cut paraffin wax, it smells like a candle. So you end up with a house that smells a bit like a candle, which is not always so pleasant. So they've actually, I believe they've taken it off the market. I'm not quite sure. The principle is good, but the delivery mechanism is the issue. So looking at phase change material here, we've got a plastic mat, which you've all got a sample of. Does anybody not have a sample of the phase change? Yep. One for you. And I'm going to pass them back to the back. Thank you. It's a plastic mat, and it's containing phase change material. If you have a look at it on a thermal imaging camera, you have a look here. This is a thermal imaging camera. Has anybody seen one of these before? You might have seen the movie Predator. Okay. He had one of these. He wasn't really seeing it. He just had a camera. A thermal imaging camera basically has a whole array of little tiny sensors called microbolometers, and they detect temperature. There's a crystal lens there that focuses the heat on it, and then it turns that into a picture. So I've calibrated it to see cold to hot between about 20 and 35 degrees, which is why people are looking white, because they're above 35. If you take that sheet there, sir, and hold that up in front of the camera for me. You see the temperature of the mat is much cooler than the room. Now that mat was in Melbourne this morning on a concrete floor where it actually refroze itself. So it refroze itself using the night air. And that's the most clever thing about phase change material, is you've got free energy. Okay, because the energy that's stored in here is just the energy that we let go of last night when it cooled off. So we're kind of like Robin Hood. We steal from the rich and give to the poor. So we steal the heat, steal the cold out of the night and give it back in the day. Or in the cooler months, we steal the heat out of the day and give it back in the night. It's quite logical when you think about it. Does anybody here have a house with high thermal mass? Yeah? And how have you achieved that?
Masonry.
Masonry. Yeah? Anybody else?
Concrete slab.
Concrete slab. Okay. Concrete's a very good thermal mass. The dilemma with normal traditional thermal masses is that they have thermal mass properties all the way from -10 to the point at which they melt. And that's called sensible heat absorption. When heat is put into a concrete slab, it gets hotter. Now what happens on a really hot day with a concrete slab?
Gets really cold.
But it gets too hot eventually.
Oh, eventually.
Yeah, and then in the middle of winter, what happens to it? It gets too cold eventually. So you have to deliver a huge amount of heat into concrete to get it up to a point at which it's comfortable to enjoy. And then once it gets past that comfortable point, you've got to wait for it a long time for it to get back again. So sensible thermal mass is good, but it's got some downsides. When it's outside the comfort range, it's not our friend. It's a slab, yeah. But if you had a suspended slab and the windows, it doesn't get that hot, yeah. Yeah, but it does get cold in winter then. Yeah, okay. So the negative side of thermal mass is that it actually doesn't help us in the wrong time of the year. The difference with that and phase change material, any kind of phase change material, is it doesn't exhibit any thermal mass property below its melt point. So below 18 degrees, this is just like a lightweight piece of plastic with some vegetable fat inside it, which is what the material is made of. So that there is just like putting a piece of concrete this thick inside your house. The difference is that once it starts to melt, it exhibits a huge thermal mass. It's about 40 times more than concrete per gram. Okay, so that's how much more energy it stores than concrete. Concrete's about 1 joule per gram of material. This material here is about 40 joules per gram across the melt range per degree. So every degree it goes up, it absorbs 40 joules. Concrete, every degree it goes up, it absorbs 1 joule per gram. Water is about 2 joules per gram when it's water. When it's ice, it's about 400 joules per gram across a very tight band. Water is one of the best phase change materials you'll ever find. The problem is it freezes at 0. And we're not Eskimos, okay? We don't want to live in that comfort band. So this is effectively room temperature ice. So we'll go back up to here. So if you have a look here, we've got different phase change materials. So we can actually, by mixing different types of vegetable fat into the little pouches, we can get different melt bands. You can imagine that chocolate melts at a different temperature to coconut butter, for example. And we can get different masses. So the more kilograms of material you have, the more thermal inertia you get. It's kind of like a truck on the highway. If it's laden with weight, it'll carry a long way once you turn the engine off. The more mass you put into the house, the more thermal inertia you get. For example, in my house, I've got 25-degree phase change material upstairs, and during a hot day, the room slowly climbs from 19 degrees to eventually hit about 25, 26 degrees by the end of the day. Now upstairs it used to get to 35, 36 degrees. Now it doesn't get past about 26, 27 in the middle of summer. Overnight, I just open the windows up and the night air comes in, provided the night air is below about 22, and the night air will refreeze the material back again ready for the morning. And while it's refreezing it, I'm enjoying the room at 22 degrees because it's releasing the heat. So it doesn't have a negative effect on the comfort of the home.
This might be in the ceiling.
Just the ceiling, yeah. I would love to have it in the walls too, but I don't want to pull my plasterboard off. Yeah, so if you want to go just ceiling, you can go a bit thicker. The thicker you go, the more thermal mass you have. You can't really put too much in. This is a church that got converted into a house. They put a lightweight extension on top. Lightweight extensions are great because they're inexpensive to build, and you don't have to worry about support for steel to hold concrete slabs up to get thermal mass, which makes your house comfortable. The problem is that you've got no thermal mass, so therefore your building swings in temperatures. If you have a building on a hot day with no thermal mass and you open up the doors and the heat comes in, then you close the doors, it doesn't matter how much insulation you have, it's hot inside. And you can't get it out unless you pump it out with an air conditioner. The difference is with phase change material, you open the doors on a hot day and you close the doors again, the material will suck all the heat out of the room and bring it back to 22 degrees again, depending on where it is in its melt cycle. So it's like an air conditioner, but you can't hear it, like the one you can hear up the back there. Okay, in the same way, in winter time, if you have a warm house, let's say you've got a fireplace going and you've warmed up the ceiling with the fireplace, and then you open up the doors and all the cold air rushes in, and then you close the doors again, the house heats up again because the ceiling is melted and it has to reset to a solid to release its heat. This is the principle of phase change material. It's basically just stealing the heat and giving it back when you need it, or stealing the cold and giving it back when you need it.
And not like concrete where if it heats up too much,
Then it's a pain.
time constant.
You don't want it. You don't want it, exactly. So the good thing about phase change is if you've got a badly designed house, you still get a great benefit. In Melbourne, we have about 200 days per year where we don't have to heat and cool a house. I imagine it's probably fairly similar in Sydney. With phase change material, at my house, it's jumped up to about 300 days per year where I don't have to heat and cool actively. I can just steal the cold of the night and I can just steal the heat of the day and just give it back when I need it. And all I do is I manage curtains and windows. It's very simple. Hot day, close the curtains, close the windows. Night time, open the curtains, open the windows, let the heat out. So it's like a very, very slow air conditioner. I'm charging it in the day and I'm releasing it at the night. When I look at the middle of winter, I want to keep it all closed. So I'll keep the curtains open so the sun can come in and a bit of heat will charge the ceiling. But if I don't get enough from the sun in the middle of winter, I light my fireplace. Or I could run my air conditioner in reverse cycle mode in the middle of the day.
But you said that the air temperature has to be 22 degrees or below on a part. What happens on those hot summer nights where
Yeah,
it doesn't get
that's a good point. Okay, and that's a good point. You can get onto the Bureau of Meteorology website, and David can help you with that if you don't know how to do it. And within it, you can actually put your region in, and you can tell it how many nights per year does the temperature not fall below 20 degrees, and you can count them. Okay, and you can say, right, there's 16 days here in Sydney where the temperature at night doesn't fall below. Those nights, the phase change material won't reset itself. Okay, then you could put more mass in so that you can get through 2 days. Okay, and if you might have 2 nights in a row where it doesn't get below 20 degrees simultaneously, you could have more mass and get through 3 days. It's quite possible to go through the entire year without actually having any heating and cooling if you have enough phase change material.
I just want to point out the thing that
Yep.
you referred to there. The thing to search for the Australian Bureau of Meteorology is heating days and cooling days,
Yep.
and that will get it. That will help you find it.
Yeah, that's right. So,
Now you talked about putting the air conditioner on in the winter in the day to warm it up.
yep, you can do that.
It's true at night. In summertime, you could use off peak after.
Yes, exactly. You can pre-freeze the house. In Queensland, what we're doing, we're talking with the Queensland government, and their dilemma is that people get home from work at 3 o'clock, because they're Queenslanders, so they get to do that. And they all put their aircons on at once because it's stinking hot and they had a hard day. Fair enough. The problem is the grid can't handle that. So they have to put a big grid in with a big power station to feed the power for that 4-hour window from 3 p.m. till 7 p.m. And that's expensive, which adds cost to the people, the taxpayers, and adds cost to the new land being released. So what we're doing in Queensland is we're using solar panels on the roof to run the air conditioner while they're at work, which is free electricity. Pump the heat out of the phase change material in the middle of the day, get it down to 20 degrees. They get home, turn off the air conditioning, and the house is pre-frozen at 20 degrees, ready for them to enjoy their night. So free cooling in Queensland. Okay, much better than paying for 38-cent shoulder tariffs and things they've got now.
What's better, if you had a flat roof, on the top of the roof, underneath the...
Okay, the question is, where's the best place to install phase change material? Closest to the people. So in between the plasterboard or the timber lining and the insulation itself. Because you're trying to control and stabilise the internal temperature. You're not trying to control the external temperature. You can in extreme climates like Port Hedland, Marble Bar, you can put phase change externally as well, and that'll resist the heat getting to the insulation in the first place, and the night desert air will refreeze it, so it will give it a better thermal property. But for the most part, you don't need to do it. You see here's a church that was done in Ashborough, North Carolina, where the temperature fell dramatically after putting phase change material in with new insulation. Huge energy savings. This is a very interesting graph. This really sums up what phase change material does. If you have a look here, the ambient temperature falls here down towards, say, what's this, 10 or 11 degrees over here overnight. It's a pretty typical cool night in maybe spring or autumn. And then it climbs through the day. Eventually it hits up here around 31, 32 degrees. With an insulated home, the insulated home lags behind the outdoor temperature because insulation just slows the transfer of heat down. So the heat transfers through, the house eventually gets cold, you've got to put a heater on through here, and then you get to here again and it gets too hot and you've got to put an aircon on through there, or you just put up with it, which is probably what some people do. With phase change material, here we're releasing heat, which is keeping you warm. So we're not getting below here 21 degrees or so. And then here we're absorbing heat, keeping you cool. So simply by using the natural process of melting and resetting, we can actually stabilise the building temperature. And the way that you do it is you simply use your windows and your curtains. It's that simple. And if that's not good enough, you can use your air conditioning on reverse cycle mode to pump heat in or pump heat out. A very small air conditioner can do an enormous amount of work. We have in my house, the living area is about 50 squares. It's quite big. I've got 5 kids. We used to use a lot of electricity. My electricity bill is about $1 a quarter. Okay, and that's thanks to solar power, which helps produce my electricity. It's also thanks to the fact that I hardly use any heating and cooling. But I do have an air conditioner there because I do like it cool on the stinking hot nights. So on those hot nights, I put my 2 kilowatt air conditioner on and I pre-freeze my ceiling overnight on off-peak rate to get it ready for the next hot day if the night is actually above 20 degrees. This summer, I think I used the air conditioner 4 times to do that. So a single 2 kilowatt air conditioner, I used it 4 times across summer.
That's very interesting. Just to check my understanding of it,
Yep.
like normally you design an aircon for like about 120 watts per square metre,
Yep.
uninsulated or fully insulated.
Yep.
For good insulation, maybe 80 watts per square metre.
Yep.
So if you've got insulation with a phase change material,
Yep,
then you
much
could
smaller.
lock that again.
Yeah, much smaller. About dollar for dollar. So every $1,000 you take out of your aircon, put it back into phase change material, and you'll end up with the same performance of the building easily. But there's no running cost on this. This has a design life of 85 years.
85 years.
Whereas an air conditioner has a design life of probably 10 years before you've got to replace it and maintain it, and you've got to pay the electricity bill as well. So you can greatly enhance the building's performance. Go ahead.
You've got a layer of plasterboard between your phase change material and the room.
Yes. Yep.
Isn't that just a bit too much insulation in the
No,
material?
plasterboard doesn't have much insulative value. It's about R.5, depending on the thickness, whereas the insulation on the other side of it is R3. So you have a huge amount of resistance to heat flow on this side, phase change material, then a little bit of plasterboard. Now, in fact, if you look at the plasterboard, if you take the thermal camera here, take this here, that's a good place to put it. Tin ceiling here. If you put that on top of the tin ceiling up there, I don't know if we can do that, maybe just hold it up there. There's no thermal mass in tin, it just passes straight through. So if you look up at the ceiling here, yeah, so you can see, oh sorry, I can see it quite well, but you can't. Okay, so what you see when you look at the plasterboard ceiling is you actually just see these blue dots all over it because the plasterboard is in connection with the phase change material and it's just drawing the heat through the plasterboard. And by the end of the day, the material might have reached 24 degrees, 25, depending on how well designed the building is and how hot it is outside. It's not a miracle product. It can only do so much, okay? And the more kilograms you have, the more energy you can resist and the more you can store. So a well-designed building needs less phase change material. A badly designed building needs a lot more.
So how do you know what kilograms?
Okay, good question. So calculation. If you look on the back of your brochure, you'll see that there's a measurement at the bottom of the table of each of the different columns, which is kilowatt hours per square metre. Can everyone see that? So kilowatt hours per square metre is how much energy you have to put into the material to get it to transition from frozen solid to be totally melted. So if you look at, let's say, the middle product in the middle column, because it's easy to find. Actually, we'll use the one that you've got on your laps there. Excuse me. This one here is Q23M27. So it's the left-hand group of I think that's orange, is it? Is that right?
Yes.
Yep. And the left-hand column is the M27, which is the lightest one. It's only 1.5 kilos per square metre, so it's very lightweight. You can put it anywhere. If you look at that material, at the very bottom it tells you it's 0.085 watt-hours per square metre. So if you have, let's say, 100 square metres of this product, 100 times 0.085 is 8.5 kilowatt hours worth of thermal inertia. So a 10 by 10 metre square, so from this wall to here and out to there again, in that area there, if I put an electric heater on in this room, a 2000 watt heater, it would take about 5 hours for this room to get above 25 degrees because it would keep absorbing the heat that you were delivering to the room. Okay? If I didn't put the heater on, maybe I put it on 1000, it'll last 10 hours. It's just the heaters are stimulating, well, maybe I've got windows with a lot of sun hitting them, same thing. Same thing with the cooling side. It's if it's full of energy and you open the windows at night, if you open windows on a house, you get about 30 air changes per hour, typically. So you open the windows up, the air comes in, the air might be 18 degrees outside, it'll refreeze the material back to 18, 19 by the time it gets to morning, because there's enough air changes to do that typically. And by then your ceiling is frozen again, like you've got the sample in your hands. and then you close the curtains and you close the windows, and the house stays really cool because it's absorbing all the heat, keeping you cool. So how to calculate it? You can just use the kilowatt hours. And if you have megajoules, like you might have done an export from First Rate or Accurate or BERS, you can export real data from a house that's been designed and modelled inside design modelling software. Does anybody here use design modelling software? Thermal modelling software? A few guys? Yep. They know what we're talking about. Ask them afterwards. But you can build your house inside this software, and it tells you how many megajoules of heat you're having to deal with per room on the worst day of the year and the best day of the year, etc. From that, you can calculate how many kilograms of phase change material will undo that heat or undo that cold. This is an example of a test facility, just passively controlled, so no controls at all, just letting it do its own thing for a whole year. So not opening windows, not closing curtains, nothing at all, just letting the house or the building control its temperatures by itself. You see here that the green building uses much less energy to stabilise. This is an air conditioner runtime test. You can see here the normal air conditioner hits 2 o'clock in the afternoon and it's just flat out trying to pump all the heat out of the room. So you've got to have a big air conditioner to overcome that. The phase change building is pre-frozen, so it's half the work has been done when it's much more efficient. You know, an air conditioner works much better when it's cold because it doesn't have to reject the heat outside into the heat, it rejects it into the cool. So if you put your aircon on at 7 in the morning, it's much more efficient at pumping the heat out of your house than it would be, say, at 2 in the afternoon because the temperature difference. So you pre-freeze, use much less electricity. You could buy a smaller air conditioner, save yourself some money there, and then the aircon doesn't have to work so hard. There was a restaurant in Taiwan and they had a real problem. In the middle of the day, they had 1,000 people come into their little wok frying restaurant, and a lot of woks going off and a lot of heat coming in. The doors would open hundreds of times. The restaurant would just get to about 30 degrees within about half an hour. No matter how big an aircon they put in there, they just couldn't get it cold enough. And they couldn't get a bigger aircon in because they couldn't get enough power into the shop because they would have had to increase the size of their mains. So simply by suspending 2 steel cables through the middle of the restaurant and hanging a little curtain blanket and laying the phase change mats out, you can imagine what would happen. It's just like hanging a concrete slab through the building. So the more of this they put in, the more thermal inertia they got. So they could pre-freeze it before everyone got into the restaurant, and then when everyone arrived, the heat would gush up to the roof, pass past the curtain on the way to the aircon return, and be pre-cooled. So the aircon worked a lot better, and obviously saved them a lot of money too. So a really good way to use phase change material is to help an air conditioner, an old one, work much better, or a bad one work a lot better.
Can I ask you about the more effective when there's a big
Just 1 second. Go ahead.
Can I ask you about that chart on the bottom? I mean, what is that actually showing?
This is showing how many times the air conditioner is coming on during the day because of the phase change material helping it.
But is each time, each gap, when the
Excuse me.
material is changing phase and back again?
No, not at all. The phase change happens throughout the day. So what's happening here is the aircon's coming on. It's realising it's not that hard to get it down to the temperature because the phase change is doing a lot of the work for it.
the normal cycling.
The normal cycling of an aircon. So it comes on, it cools it, it realizes, I've got to 22, I'll turn off again. Because the phase change is helping the return air be cooler.
So it's gradually liquefying.
Eventually it's liquid, but by then it's nighttime.
Right.
And the natural night air can refreeze it, or you can put the building on night purge mode. Just ventilate. Like this Telstra building here, overnight, if they had the phase change through all the ceiling space, they could just put the building on ventilate overnight, push all the night air in below 20 degrees and pre-freeze the building to 20. Then during the day, the aircon only has to pump a little bit of heat out because the phase change is going to absorb all the heat first. Go ahead. Yep.
If you have walls, say mud brick walls or solid brick walls like that in Perth,
Yep.
obviously the only place that you can put it is in the ceiling. It's still going to be affected in the ceiling rather than in the walls.
You need to model it. You need to consider it's not magic. It's just more thermal mass in the comfort band. So if you've got a very badly designed house, you need to do other things as well. So this is another test facility proving that phase change material saves energy. You can see here there's a lot less power used because the phase change material is simply melting. If you want to get into the modelling calculations, this is in Fahrenheit, so pardon me for that, but if you look at the comparison of a wall, if you measure the time it takes for heat to pass through a wall, you can calculate its R value. The test facility is at Fletcher's Insulation in Sydney here. We ran a test on phase change material. Normally you put an insulation mat inside the machine. It stabilises the temperature at the top, I think at about 30 degrees, and it has a sensor at the bottom at 20 degrees. It stabilizes the insulation, then it does a test, and it cycles it and measures the R value. It comes out with R2 or R3. It takes 20 minutes normally to stabilize, and then it takes about half an hour or an hour to do the test. We took phase change material and put it in there to see what would happen, because we wanted to get an R rating on it. Well, it took 7 hours to stabilize. And then the machine just came back with error. Because the heat kept going in and it wasn't coming out, so the machine figured there was something wrong. So if you look at a wall, if you look at the comparison of insulation, now this isn't insulation, so you can't confuse it with replacing insulation. But if you look at a typical day, if the phase change material doesn't completely melt, the R value of the wall, this is US R value, so divided by 6. The R2.3 wall is actually R25. It's a pretty big difference, because the thermal energy is not passing through and changing the temperature on the inside, provided it doesn't melt. If it melts, then it just goes back to R2. But by then, it's night time. Okay, there's different ways you can apply it. This is a re-roofing mechanism where you basically take an old tin roof, lay the battens down, lay the sheets inside, put some bats on top, and then put another layer of tin down. There's lots of ways it can be used. You can see here the heat flux of the roof before and after. Heat flux is just passing of heat through. In a restaurant, we explained that before, just on top of the ceiling tiles, a simple installation is just rolling the mats out, and then the building has much more thermal inertia. You can pre-freeze it or preheat it. Here's a control situation where they had 2 takeaway restaurants in the same town, experiencing the same weather, built the same way, facing the same direction, with the same number of people per day. So it's a great way to test phase change material. You can see here the BioPCM store here used far less energy because it was able to use the phase change material to help the air conditioner work better. The upside is not just about money either. Imagine a house that was always 21, 22 degrees when outside it was 30 degrees or outside it was 10 degrees. You come in and it just feels really comfortable. You don't have air conditioner blowing air on you. You don't have dry air. And you can preheat or pre-cool it before you get home to experience that. You can see here, this was actually the test restaurant that was done with the curtain. See the improvement here before and after. The green is before and the blue is after. Here's another area with a kitchen. The kitchen temperature was suffering dramatically because the aircon couldn't keep up, but the phase change kept it stable. The product is used in the US in a whole lot of different manufacturing materials. It hasn't been made into any materials in Australia yet. The typical return on investment for someone who installed phase change materials is between 6 months and 5 years. We had one situation where the payoff was about 3 days. So it all depends on what your cost of energy is and what the problem you're trying to deal with is. This application was a military tent in the desert, and in order to cool the tent to keep the generals cold, they had to have a generator running to run the air conditioner, and it was in a war zone, so diesel was $1,000 a gallon. And the night was 0 degrees and the day was 40 degrees. So straight away you got a perfect situation for phase change to refreeze itself passively and remelt itself during the day. So you get fast payoff sometimes it's slower. No matter how you look at it, you don't have to buy anywhere as much energy per year if you have phase change material. You can do big houses, you can do small houses. These guys here have got these little granny flats, I guess you could call them over here, with a solar power system and phase change material. They've got the energy bill down to $15 per year. It's being used in colleges over in the US, universities. Here's a way that it can be used intelligently, like being built into a building design. So here we're using the night air to pre-freeze it and exhaust the air, rather than actually letting the air in and out again. So there's lots of different ways you can actually charge and discharge the phase change material. Harvard Graduate School's got some in some of their buildings for testing. So it can be used in different types of fabric in buildings. We just won the tender in the US for the Olympic archery stadium. Now, why would you want to use it in an archery stadium? Because you don't have to have an air conditioner running, which blows the arrows off course. So the phase change material was cheaper than the air conditioning system with no running costs, because the night air was cool enough to refreeze the material and give them a stable temperature during the day. It's integrated into a steel panel here, so the steel panel, which has almost no thermal mass, all of a sudden has a huge thermal mass. This is a board product where we've got a timber layer, insulation and phase change, and then foam and then foil and insulation. That barrier there, you almost can't get heat through it no matter how hard you try. You can do it in wall panels. You could even lay it inside concrete into sandwich panelling to improve the thermal mass of the concrete wall. Energy modelling, for those guys who use Accurate, Burrs and First Rate, there's another program called Design Builder, which you might have heard of, which has actually got phase change material listed inside it now. So you can actually look up each material, each mat, and work out how many kilowatt hours it will change the building by. So you can actually model the house without phase change material or the office, and you can tick yes, insert the phase change material and see the difference based on the climate zone and all the other attributes of the building to see how much energy you won't have to use. So I won't go too much into the technical detail, but in essence, phase change material is a way that you can have a much more comfortable building, use much less energy. It's quite warm in here right now. In fact, we can probably work out how warm it is by looking over at the wall. It's 26.1 degrees in here. So go ahead.
The temperature range in which the material freezes and
melts. Yep.
Is about 22 to 26 degrees, is that what you're saying?
It varies. If you have a look on the back of the brochure, the question was, does the temperature range vary? Let me use that. If you have a look on the back here, there's 3 different temperature ranges. There's the orange, green and the blue. The orange one here has an 18 to 23 degree range. You see it on about the second or third last row on the spreadsheet. And the next one is 20 to 25 degree. And then we have a 20 to 27 degree. This one here, I brought it up especially. That's a 16 degree phase change. So that one there starts changing at about 8 degrees and finishes at 16 degrees.
So it's changing phase right through the temperature range.
Yeah, if you feel that there.
And that's according to the mix of material?
You pass it around. That sheet there was on my warehouse floor this morning in Melbourne, so I brought the weather with me. If you have a look at the temperature of it, you can probably see it over there as it goes passed around. Probably track it actually, can you see it there? Okay. You're just not safe, are you, with phase change material? Okay, so is that okay? Yep.
Yeah, so how does that latent heat compare to the latent heat of water?
This has the latent heat of water about half of water.
About half.
Yeah, so water is the best.
At the ice?
Yeah, water is best at 0.
Yeah.
Phase change is best at 20.
Yeah.
Yeah, because water is about 2 joules per gram throughout 0 to 100 degrees. In fact, to get water from ice to a liquid is the same amount of energy to get it from 0 to 80, to give you an idea of the change. So,
It's 4.2 actually.
4.2, sorry.
Yeah.
4 times. Go ahead.
You define phase change materials as those that melt and
reset.
solidify within the range.
Yep.
But surely you should include as phase change materials concrete and water.
Yeah, everything's a phase change material.
Yeah.
Eventually it'll melt, and eventually it'll freeze.
No, but I mean,
Yep.
even without melting, water can be a phase change, and concrete can be a phase change.
Yeah,
The
the phase change, if you look at it, I don't have a whiteboard here, but if you take, I'll pretend I've got a whiteboard, okay? It's my whiteboard finger. If you take normal water and you heat it, it gets hot. Everyone agree with that? Yep. Sensible heat absorption. You put heat in, it gets hot, it's sensible, it makes sense, okay? Latent heat absorption. You take ice and you heat it, and what happens to it? It doesn't get hot. Eventually it melts to a liquid, then it goes up again, then it hits 100, and what happens? Flatlines again. Okay, that's latent heat. It's when you're putting heat in and it's not actually getting hot because it's using all the energy to change the structure of the material. So your question is, isn't water a phase change material while it's liquid? No, it's not, because it's not changing its structure. You put heat in, it gets hot. It's when it changes from a liquid to a gas or from a solid to a liquid, that's the phase change point.
Yeah, but
Maybe we'll take it afterwards.
the heat that it's emitting or the coolness,
Yeah.
that has a phase change over time. I mean, if you have a very thick stone wall,
Yeah, it releases heat, but it gets colder while it releases it. That's the difference. That's the fundamental difference. A good question. If you get concrete and you put it outside on a cold night, it will release heat, but it gets cold. This releases heat without getting cold. That's the difference.
we're interested in the environment rather than the material. You know, the temperature of the room.
Sorry?
That is not called a phase change.
No, it's not. It's not a phase. Phase change is when it changes state and it releases heat or absorbs heat. John?
I understand your point.
Yeah, good. Nick?
That's very interesting.
examples that you showed, mostly were church in North Carolina or some house in California and so on. Are there any residential dwellings in Sydney where this is being used? So
there's one being installed next week in Paddington.
Paddington.
It's very new. This is new technology. You guys are like at the point when they released microwave ovens. Okay? Everyone's been cooking in a stove all their life and they're going, what's this microwave oven? It's the same thing. It's now available. You can buy it. Everyone's wanted phase change for a long time, and now you can buy it off the shelf. And that's why there aren't many test cases in Australia yet. Hasn't been here long enough.
You can tell us something about the dollar,
The cost? It's all on the website, the costing, and there's a calculator on there that starts at $43 per square metre.
Okay.
That's the retail price to an end user customer. If a builder has to buy it, he gets a bit of a discount, so you never pay more than that.
Okay.
Go ahead.
Thank you.
Can you explain when you would use the different materials? Like, why would a material that melts and freezes at 27 degrees be useful
Where do you live?
in Sydney?
What's the weather like here?
Well, you know, typically it's in the 20s.
Okay, so what about if you lived in Townsville? You mightn't get a night refreeze. You see, so if you have a material that refreezes at a different point, you can refreeze it passively. So it depends if you're having an active design or a passive design, and it depends on what temperature you want the room to be. There's a bit of a sweet spot.
It's a trade-off. You know,
It's a trade-off, yeah.
In Townsville, you're happy for 27 because at least it freezes.
Because at least it's only 25 in the middle of the day when everyone else's house is 35. Yeah.
Whereas here we would normally use the orange one.
Yeah, well, it depends what you like. If you use the 23 degree product, it needs to get down to 18 degrees to reset, which means less days per year it'll passively reset. And also it depends on where you're putting it. If you're having it in a bedroom, you might like it cooler. I like it cooler in the bedroom but warmer in the living room. So you can put 23 in the bedroom, 25 in the living room, and maybe use an air conditioner in the middle of summer to pre-freeze the bedroom before you go to bed, a small 1 kilowatt unit that you might already have there. So there's 100 combinations of it. The big question is, what's the comfort band you like? Because it spends most of its time in that band between 18 and 23. The sweet spot on that one is 20.5. That's where it likes to be. If you like that temperature, go 23. But remember, it's got to refreeze itself with a night air. Yeah?
Yeah, I'm just wondering, I noticed on that sample that's going around, it's moist because it's cold and it's condensing, it's got condensation on the surface. So what happens if it starts like dripping water onto your ceiling tiles and stuff?
It's unusual because that's actually very cold and it's been put into a hot environment. So it's just the water's just beating on the outside because it's at dew point. So it's a good question, but in a normal environment, the building temperature would be adjusting at the same rate as the phase change material because the room would be getting hotter and the material would be resisting it. So there wouldn't be a differential there. It would only be if you took it outside and froze it overnight. We thought about this, the pensioner's heater. You know, you could take it outside at night, cool it off and bring it inside and put it over your legs in the summertime for your low-cost air conditioner. But yeah, that's the reason. Go ahead, sir.
Given that this kind of material only change between this certain degree, so if we got enough budget, and is that correct? The more we put in to house,
the more you put in, the more inertia you get. Exactly. The longer it carries it for. At my place, I've got the M51, which is the middle weight, middle temperature in the upstairs ceiling, and for 7 months we haven't used an air conditioner or a heater. Not once. Don't need it because there's enough cold in the night to release just by opening windows, and there's enough heat in the day to charge to keep it warm at night. So just by managing those two things, you can actually get rid of a lot of heating and cooling loads that you'd normally pay for. You don't wake up in the morning, the kids aren't freezing in their bed anymore because the materials are releasing heat all night. So it's much more pleasant to be in the home, and there's no wind and there's no noise and dry air.
I was thinking about it, we've mainly been discussing from a cooling point of view. That was the warming point of view. If you're using it for warming and you've got a timber floor, can you install it under the floor? Would it work quite well there?
It's a good question. The question is based around the idea of why don't we put more thermal mass in the floor, because that's what we've always believed. Thermal mass goes well in a floor if it's concrete because it's heavy, and the reason for that is it's too expensive to put it above us. The right place for it's above us. It's never been put there because it's always weighed too much.
Even if it's heat, the heat's trying to rise all the time. Like if you've got a fairly high ceiling, because Renew magazine a couple of issues ago was quite critical of the heat and ceiling concept.
Yep.
So,
but remember, this doesn't have any thermal property above 25, and it's resisting the room getting warm all the way up there.
Yeah.
So if you had
about in a winter point of view, and you're wanting some warmth retained in the room, wouldn't it be better to have it down lower rather than higher?
Yeah, but the warmth will come upwards anyway. So what we find at our place is that if you close the curtains and the ceiling is charged, like we've got one of those Canara fireplaces, throw some logs in that, warms us up while we're watching TV, go to bed, fire goes out, and we wake up in the morning, the house is still warm because the curtains are drawn and the ceiling is warm and the insulation's above it. So there's nowhere for the heat to go. So it just slowly passes through the insulation. So it's quite simple to keep your house at 19, 20 degrees by the time it gets to morning, just using a fireplace in the worst part of winter. And you can do the same with a reverse cycle heat pump. You could preheat the house during the day in the middle of winter using your solar panels running your aircon directly, pre-warm the house to 23, sun goes down, turn off your aircon, means you haven't used any carbon-based electricity, and you go to bed and your house is just slowly refreezing, and while it's doing that, it's releasing the heat.
I recall about 25 years ago in commercial
It's a long time ago.
air conditioning, they trialled phase change material ice balls, they were called,
Yes.
at Darling Harbour.
Right.
On the
Okay.
new constructions down there. And they were notoriously unsuccessful.
Yes.
I can't recall.
The reason was the material degraded over time. That was the dilemma. The material, it worked brilliantly, but it failed.
So are we talking, was it glycol or something inside?
I think they used salt-based products. I think it was potassium chloride salt with... I don't know what the reason was that it failed, but it was supposed to last 10 years and it lasted 1 or 2 years. So the product got a bad name because the material didn't work, which is why they went to the trouble. The people who developed this in the US have been developing blood transport products and food transport products for 30 years. And they want to keep the blood at 4 degrees while they transport it. So they had to find ways to encapsulate the material so it didn't break down, and the right materials that they lasted a really long time.
I detect that 4 degrees is beer temperature.
Beer temperature too, yes. But ice is better to cool beer down because it's twice the thermal mass.
So could you use this material inside commercial?
Yeah, there's so many applications. I had a guy the other day, he goes, "This is what I need." And I said, "Why?" He says, "I've got a welder and he's diabetic. And he's working in the hot tin shed and it's too hot for him. He has to keep coming in and sitting in the air-conditioned office to have a half-hour timeout. I can make a jacket out of it and put it in the fridge and make him keep working." Same thing in a mining shed. Like the guys who work on those huge trucks with the big wheels, they're out there working in 40-degree days. If that truck's off the road for an hour, it costs the company $10,000 or more, probably. If you guys can work because they've got a phase change jacket, they can work right through the day for the cost of some material in a fridge. Go on.
Is this one UV stabilized?
UV stabilised? No. No, it'll eventually break down in sunlight. It's not supposed to go outside. So just one. You've got 2 questions. Go on.
Talking about floors, I mean, most houses, new houses now have double story.
Yes.
The upper floor is lightweight.
Yep.
If planned properly can get them into sun.
Yeah, you can do that. It's a great place. Yep, and you just use some Tek screws and screw it up into the floorboard or staple it into the timber. And you can do it on a new build, but often you can't get in there on an existing home. So on a new build, then it's a good place in the ceiling of the floor below because it gives the building thermal stability and it's all tucked away nicely in the insulation envelope.
And just on what you mentioned just on longevity, you mentioned an 85-year design life. What sort of warranty?
We give it a 7-year warranty. Yeah. The plastic itself there's 14 different layers of plastic in there to encapsulate the vegetable fat. And there's a fire retardant to stop it burning and a gelling agent to try and keep it together in a putty when it melts. It's not toxic, you can burn it, it just releases carbon dioxide gas. The plastic itself melts away fairly quickly because it's got no real thermal energy in there. But the material itself actually tries to put fires out, so it has a negative effect on fires. Go on, sir.
Are builders finding any practical problems, like if there's penetration through that, you can have leaks?
Yeah, we've had one case where somebody got a leak in the product. When he was installing it, he was not careful with his scissors and cut one of the pouches open. So it can happen, but the downside of having to repair a small patch versus the upside of having a house with no power bills is a pretty good trade-off.
What happens does it leak out or?
No, it explodes. No, it doesn't really. It's a vegetable fat. So if it got onto plasterboard, it would soak through and maybe make the paint peel a bit.
So could you just tape it up with some?
Yeah, just cut it out and replaster it.
Yeah, if you've got a hole in it, can you just...
No, you just cut that square out and just chuck it away, yeah. It's only one little...
I was just thinking about that heavier one you had before that.
The big one, yeah.
16, if you've got a leak in something like that, could you patch it in any way? Or just...
You probably could. Like, it doesn't really perish over time. It's just vegetable fat. Like olive oil, I mean, that lasts for a long time. Yeah. But you're better to cut it out if you do damage it. Go on, Matt.
I think I you're in a house, an old house with wooden floors, and the main thing you want to do is heat the house in winter rather than cool it in summer.
Yep.
Would it be any help to put it underneath the floorboards?
I don't think so. I think it's easier to put in the ceiling. It's much faster.
Yeah, but the heat doesn't come down.
Put a ceiling fan in. Yeah, just stir up the air. So you let the heat from, you've got a fireplace, have you?
This is in a bedroom.
Okay, well, if you have a heater going in there in the middle of winter, then it'll charge the ceiling, and then the ceiling will stay warm. As long as it's insulated above, the heat will have no choice but to warm the room. Yep. Go on, mate.
Is the heavyweight stuff like the 0 to 16 thing you were showing me? Like the 16
Yeah, that's the heaviest one. That's actually not on the brochure. That's a new addition to the family. My wife had a baby last week too. New addition to the family. There's a column that's not there, which is M182. That's M91 on the right column. So M182 is double all those values.
So was that like 10 kilograms per square metre?
10 kilograms per square metre, exactly right, yep. And then you can choose temperature ranges. The ones that we have standard are 23, 25, 27, but we also have anything else you can imagine. We've got 16 degree, 4 degree, 37, 42, 49, 67. So you could do a thermal storage tank for a hot water unit. Imagine this, 50 litres of phase change material in a stainless steel tank with a copper coil around the outside. That's equivalent to 500 litres of hot water. So you could bolt your hot water tank to the wall. Really good for when you've got a small building envelope to work with. So a lot of things phase change can do if you just think about it.
Just third question.
Go.
I just wondered, has any life cycle assessment been done on this, comparing it to air conditioning running costs or anything like that? And its manufacturing embodied energy and everything?
Well, there's not very much embodied energy because we have to grow the vegetable fat, so it's much better on that side. As far as how many kilowatt hours per year is saved, it depends on how well designed the building is and how much air conditioning you're offsetting. So that's why we say anything from 6 months to 5 years is a typical financial payback, which is probably also a carbon payback.
You have a 7-year guarantee on it.
Yes.
Is the melt and freeze process fully reversible? Does it lose its ability?
No. 85. It's tested to 85 years.
Yep.
With 1 melt cycle, 1 freeze cycle per day through an accelerated test facility. So heated it, melted it, lost no mass, lost no performance over 85 years. They gave up. They said that's enough. So we don't know what will happen after that, but I'm okay with that.
I'd like to take the opportunity from the floor to ask a question myself.
Go ahead.
And then I'll ask. I'd like to ask a question myself, and then I'll ask David to close.
Yep.
One question is, since we can put it in walls and can have it on roofs, is there any research to show what I heard was related to people's feeling of comfort, which is it tends to be a perceived heat thing. Yeah. So like if you're moving in a volume, you've got air that moves past you and stuff, but part of your perception of the comfort is related to the apparent infrared or ambient temperature of the wall and roof. Yeah. It's not necessarily the exact temperature you're experiencing at the time.
They call it, or some people call it skin effect, where the temperature of the wall affects how you feel. Like if you walk into a wine cellar, besides the fact that there's all that nice wine there and it's great to be in there, the temperature of the wall is cool and you feel cool because the wall actually pulls the heat out of you. Like sitting beside a glass window, most windows are glass, but sitting beside a window when it's cold outside, you feel cold because of the actual solid material there. And that's why putting it on the ceiling is really good.
I'm sure we actually want to leave at this point. There's somebody who want to leave. I'd like everybody to put their hands together for Paul for such an excellent presentation.